Hi, everyone. Welcome back to another episode of the Data Science Decoded. I'm here with Nir and Mike. How are you guys? How are you, Nir? Let's start with you.
We're doing great.
I see you're in space.
I am in space, in my own world. This is a seminal paper. I'm very excited to talk about it.
Oh, perfect. Same on my side. A lot of math, but we can go around it and hopefully get the gist. How are you, Mike?
I'm okay, feeling good. I got to do some stuff fast in order to converge to 7:40 p.m. Israeli time, but I hope I managed to complete most of the stuff. And this paper is not very easy paper. I think the ideas in this paper are very, very important, but the explanations are very muddy, and it requires me some substantial effort to dive into this explanation. And I hope I managed to comprehend it at least for 70-80%. I hope so.
Yeah. Perfect. That's why we're here. We're gonna help each other, and hopefully the three of us will be able to cover most of the important parts. I agree, and as you can see, by the way, I'm not home. I'm traveling, but I'm not gonna miss an episode. So we're recording from a hotel. And from my side, I agree. Important concepts and a lot of math. But I think we can do it. At the end, actually, he has like a summary with bullet points of the important part. So we'll get there at the end. Cool. So the name of the paper is On the Problem of the Most Efficient Tests of Statistical Hypotheses. It's by Neyman and Pearson from 1933.
Yeah.
And again, the title sounds bombastic and important. So that's why we thought, okay, we should go over this paper. And if we look here, it's quite long, like 50 pages. And yeah, so in order not to break it into three parts like the Shannon paper, we won't dive deep into all the derivations. But the introduction is important, and I'll read it out loud and we're going to discuss it. So he says here, or they say, the problem of testing statistical hypotheses is an old one. Its origin is usually connected with the name of Thomas Bayes, as we know from the Bayes theorem, who gave the well-known theorem on the probabilities a posteriori of the possible causes of a given event. Okay, and funny, the causes are in how it's called? Near.
Causal, you mean?
Gershaim. How would
Yeah. It is interesting because we're not going to talk about causality theory, and what is very famous Jewish mathematician who developed. I think Nir is reading this book. We're not talking.
Pearl.
Julia Pearl. But
we won't talk about it. But they say like approximately whatever they think of causes. We won't go over or in it, but it's funny that that's how it's mentioned. They mention it. Okay, I'll continue. Since then, it has been discussed by many writers, of whom we shall here mention only two, Bernard and Borel, whose different views serve well to illustrate the point from which we shall approach the subject. So first, I thought maybe it's like Bernard Russell, but it's not. It's a different French Bernard that they are referencing here. And they say Bernard put into statistical form a variety of hypotheses, as for example, the hypothesis that a given group of stars with relatively small angular distance between them, as seen from the Earth, form a system or a group in space. So he says this, let's say this is a hypothesis. His method of attack, meaning how they're gonna decide if it's true or not, which is that in common sense consists essentially in calculating the probability P that a certain character or character X of the observed facts would arise if the hypothesis tested were true. Okay, so say if the hypothesis is true, so we should be able to measure some character P with a probability P. If P were very small, this would generally be considered as an indication that the hypothesis age was probably false, and vice versa. Bernard expressed the pessimistic view that no test of this kind could give reliable results. Yeah, Mike.
I just wanted to mention, then you're talking about calculating of probability under some condition. We are talking about null hypothesis and about something which is somehow related to p-value, which is a very famous statistical term. But we're not going to talk about the p-value, but we're going to talk about something which is similar to p-value.
Agreed. And then they continue. Burrell, however, in a later discussion, considered that the method described could be applied with success, provided that the character X of the observed facts were properly chosen, where in fact a character which he terms en quelque sorte remarkable, something in French. Sorry, my French, or excuse my French.
By the way, it is quite interesting. We have I think 3 or 4 phrases in this paper in French. And as far as I remember, there is a very famous book of Russian Lev Tolstoy, and the War and the Peace or something like that. I don't remember the name, but the half of this book was written in French. So, but I didn't know that French was popular for the mathematicians maybe 80 years or 70 years after it,
Meaning mathematician knew how to read and write in French, although they're not living in France.
That's yeah.
Makes sense, at least for me, in a naive perspective, because most of 18th, 17th century mathematicians came from France. Okay, let's continue. And we're number 5 podcast in France, so maybe that's the reason. According to statistics, which we covered here. Anyways, yeah, I won't digress anymore. Okay. We appear to find disagreement here, but are inclined to think that, as is so often the case, the difference arises because the 2 writers are not really considering precisely the same problem. Okay, so let's say now maybe they're looking from different perspectives. In general terms, the problem is this. The problem is this. Is it possible that there are any efficient tests of hypotheses based upon the theory of probability? And if so, what is their nature? Before trying to answer this question, we must attempt to get closer to its exact meaning. In the first place, it is evident that the hypothesis to be tested by means of the theory of probability must concern in some way the probabilities of the different kinds of results of certain trials. That is to say, they must be of a statistical nature, or as we shall say later, they must be statistical hypotheses. Now, just a second, yes. Now, what is the precise meaning of the words an efficient test of a hypothesis? There may be several meanings. For example, we may consider some specified hypothesis as concerning the group of stars and look for a method which we should hope to tell us with regard to a particular group of stars, whether they form a system or are grouped by chance, their mutual distances apart being enormous and their relative movements unrelated. So again, they're talking about maybe there's something can happen by chance. So we are getting some kind of probability here.
Yeah, so he's getting closer, I think, to what we call today rejecting null hypothesis. Today we are not computing the probability that some hypothesis is correct. We are rejecting some null hypothesis. We want to check some not null hypothesis, some different hypothesis by means of rejecting null hypothesis. I think he's slowly getting closer to this rejection.
Okay. If this were what is required of an efficient test, we should agree with Bernard in his pessimistic view. For however small be the probability that a particular grouping of a number of stars is due to chance, does this in itself provide any evidence of another cause for the grouping but chance? And again, something in French, comment de near de allures la singularité d'un enjeu la hasard incapable, whatever it means.
Put it in ChatGPT. Let's we can translate it now.
What does it mean? Indeed, if x is a continuous variable, as for example is the angular distance between two stars, then any value of x is a singularity of relative probability equal to 0. Right? Means like every angle you choose, the probability of it being that is 0.
Yeah, that's what Mike said. He's trying to get us into, we're not trying to compute the probability, but see how we can smartly reject the null or accept the null.
Yeah. We are inclined to think that as far as a particular hypothesis is concerned, no test based upon the theory of probability can by itself provide any valuable evidence of the truth or falsehood of that hypothesis. So again, in a sense, because we shouldn't be choosing an exact number or something like that. But we may look at the purpose of tests from another viewpoint. Interesting. Without hoping to know whether each separate hypothesis is true or false, we may search for rules to govern our behavior with regard to them. So that's interesting. We like inserting behavior of humans in the discussion, as far as I understand. In following which we ensure that in the long run of experience, we shall not be too often wrong. So to me, again, this is like the frequentist view. Right? We run experiments, and each time we think something, and hopefully in the long run, we mostly, right, that's statistics, mostly will be correct or less wrong. Here, for example, would be rejected or not calculate a specific, Here, for example, would be such a rule of behavior to decide whether a hypothesis H of a given type be rejected or not. Calculate a specific character, a specified character X of the observed facts. And then if X is larger than X0, reject the hypothesis H. If X is lower than X0, accept the hypothesis H. Such a rule tells us nothing as to whether in a particular case H is true when X is smaller than X0 or false when it's larger. But it may often be proved that if we behave according to such a rule, then in the long run, we shall reject H when it is true no more, say, than once in 100 times. In addition, we may have evidence that we shall reject H sufficiently often when it is false.
Yeah. And
yeah, Mike.
And then here he started talking about statistical power, and when you continue to read this paper, we'll start talking about the error of type 1 and error of type 2, error of rejection, false rejection of null hypothesis and false exception of null hypothesis. We are getting closer to this fundamental concepts of modern statistics.
Yeah, this is I think the first paper that in my view first ordered in a rigorous way the problem of classification. And I mean, before that, and we saw that Fisher has some tests, especially tests of I guess kind of
Which
like
test?
Sorry?
Which test? I didn't hear.
Yeah, Fisher had some tests, but it wasn't to choose between hypotheses. It was like a significance type of test. Is let's say that as an example, is these measurements Gaussian or not Gaussian? Okay. What is the significance of this? And I think that Neyman and Pearson, both of them, they introduced, they opened the field of classification, and that's my connection, at least in my mind, for machine learning and deep learning and AI, which is
meaning classifying hypotheses. That's what you.
Yeah, choosing between hypotheses is classifying. Period. And it doesn't matter if we have a strict hypothesis as when we reject the null, or we don't. And we know from statistical theory that even though he's talking about binary type of classification, this can be extended in a way. I mean, the test that he is proposing here, will propose here in the future text here, can be extended to the null hypothesis, and then H sub 1, H sub 2, and so on and so forth. So it is the theory of classification, the first paper that does that, I think, in the history.
Yeah, I tend to agree. And we are going to and I think it is the first paper which propose not just to compute. Okay, we are going to talk about likelihoods, so I'll start talking about likelihoods. So this is the first paper which propose not just to compute likelihood under some hypothesis, but compare likelihood under this hypothesis and under some other hypothesis. And it is very human. We are human. We are very good in comparing. And we are not so good in estimating odds. But if you ask me what is the odds of this one against this one, I can tell, okay, this one is more probable. Okay, and here we see our softmax. You can see any numbers in the before the softmax, and then you are just normalizing it. Okay, you have two numbers, and then you just computing the relevant power of each number relevant to each other, corresponding to each other. And I think then I read this paper. This is the first thing I thought about.
Interesting. Also an interesting connection to modern machine learning. Okay, so I'll continue. And they say, if we accept the words an efficient test of the hypothesis H to mean simply such a rule of behavior as just described, then we agree with Borel that efficient tests are possible. We agree also that not any character X, whatever, is equally suitable to be a basis for an efficient test. And the main purpose of the present paper is to find a general method of determining test, which from the above point of view would be the most efficient.
Yeah.
And by the way, he cites here Fisher soon. I don't know if it's already here.
Yeah, it's here. Yeah, down there, last paragraph.
Okay, perfect. So I'll read it now. In common statistical practice, when the observed facts are described as samples and the hypotheses concern the populations from which the samples have been drawn, the characters of the samples, or as we shall term them, criteria, which have been used for testing hypotheses, appear often to have been fixed by a happy intuition. They are generally functions of the moment coefficient of the sample. And as long as the variation among the observation is approximately represented by the normal frequency law, right, the Gaussian, moments appear to be the most appropriate sample measure that we can use. Okay, but as Fisher, the paper we reviewed in the first episode, has pointed out in a closely allied problem of estimation, the moments cease to be efficient measures when the variation departs widely from normality. Further, even though the moments are efficient, there is a considerable choice in the particular function of these moments that is most appropriate to test a given hypothesis. And statistical literature is full of examples of confusion thought on this choice. Okay, so Nir, you are...
and to make long story short, it just tells us that the method of moments is not sufficiently good for some, maybe I call it complex data distribution, which is not Gaussian.
I think it's even more than that. I think it's maybe I think of it a little bit differently. Yes, he is referring to the method of moments. I think that in general, what he's saying here is instead of happy intuition, or in other words, guessing, the statistic that we will use in order to classify between two hypotheses. He, in this paper, will present a more rigorous method in which to choose this statistic, and he will show that the statistic that we will arise out of his math is the most efficient one in terms of maximizing the power of the test and fixing the size of the test.
And it is the maximum likelihood, as Fisher promotes.
Yes, it is. It is a ratio of maximum likelihood. Yes,
exactly.
Yes.
Ratio,
which we now call. He, by the way, didn't present it as ratios, but as an inequality. But I think it's called now likelihood ratio test in statistics.
Yeah, cool.
And likelihood ratio, and when you go and calculate this likelihood ratio test, you get a statistic. You get some function of the measurements. And he's saying, let's not guess. Let's read this paper and see how to do it.
It's they are saying, right?
They are saying, Neyman and Pearson. Sorry, yeah. You're right.
And here he gives just examples. I won't go over them, but he gives specific examples of estimating the error of the difference of two random variables, and he gives specific options that happen, and now you change and tweak a little bit the equations, and at the end they say that there's a lot of freedom, right, to what happens, what to choose, and that's why they want something more general.
Yeah. By the way, it is a very simple example. I think he differentiates between two cases, and the variances of these distributions are equal and are not equal. And in two of these cases, your statistical estimate is different. And I think they ask themselves, can we do better? Can we come up with some statistical computation which is good for a broad range of, in this case, variances?
Yeah, and he says here, they say, in earlier papers, we have suggested that the criterion appropriate for testing a given hypothesis could be obtained by applying the principle of likelihood. This principle was put forward on intuitive grounds after the consideration of a variety of simple cases. It was sequentially found. Yeah, wow, that was difficult. Found to link together a great number of statistical tests already in use, besides suggesting certain new methods of attack. It was clear, however, in using it that we were still handling a tool not fully understood. And it is the purpose of the present investigation to widen and, we believe, simplify certain of the conceptions previously introduced. we shall proceed to give a review of some of the more important aspects of the subject as a preliminary to a more formal treatment. Okay, so they say some prior papers introduced similar ideas, but they were never like formalized as they do here. Also, it's funny when they use the method of attack. Today, that pass review, right? It's too inflammatory.
It's not an adversarial attack.
Yeah, cool. So now we are chapter number 2, outline of a general theory. So they say, suppose that the nature of an event E is exactly described by the values of n variates. So there's x1 to xn, and they say that each x is sampled is a random variable, so it's sampled from some distribution. And then they say here, suppose now that there exists a certain hypothesis H0 concerning the origin of the event. Event, again, it's the n random variables. We got a sample of each one. Which is such...
I think... okay.
Yeah, sorry.
No, go ahead. Go ahead. I remember what I wanted to say.
Okay. So again, we have an hypothesis H0 concerning the origin of the event, which is such as to determine the probability of occurrence of every possible event E, and they define it as P0. It's the probability that H0 is true, given all the random variables between x1 to xn.
Yeah, and a very small point for our listeners who are scared by these multiple integrals. It is not so complicated. It's just looking at this sample of n terms, which is sampled from H0, and H0, the nature of events is actually defined by distribution. We term it as a distribution today, and it's just looking at this sample of n points as a point in n-dimensional space, because each point is a scalar value, and here it just defines an integral which actually computes the probability of such not such event of the event which this n-dimensional point belongs to some subspace of this n-dimensional space. I hope I didn't get this too much complicated.
Yes, just to maybe add on what Mike said, P naught or P null is P sub 0 here is a PDF. It can be seen as a probability density function. Okay, and capital P naught is basically a probability, or the integral, the n-dimensional integral on this PDF.
Mm-hmm.
Which is if we have the CDF, the commutative, which can just put these x1 to xn in and calculate it. But this is a way of integrating.
Yeah, thank you for the points. And they say that the integral all over capital W, which is it's our space where we live in, is equal to 1. So they wanted also the probability to be normalized. Now they continue. We shall be concerned with 2 types of hypotheses. So in the paper, one is what they call a simple hypothesis, and the second one is composite. The hypothesis that an event E has occurred subject to a completely specified probability law, which is the probability function, P0, P null, is a simple one. Okay, so they say when we know exactly the probability distribution, that's a simple problem. While if the functional form of P0 is given, though it depends upon the value of C unspecified parameters, H0, the hypothesis, will be called a composite hypothesis with C degrees of freedom. Okay, so again, let's assume, and they show here a Gaussian distribution. So if we know the parameters of the distribution, it will be a simple problem. And let's say we don't know the mean. It's
composite.
Case alpha, and it could vary. Then it will be a composite problem. Okay, and they distinguish them because it's more difficult to do the latter. Yeah, sorry, Mike, I'm with you.
It's okay. I want to emphasize that it is an extremely important point of this paper, because the composite hypothesis, one of the main achievements of this paper is the formulation of statistical tests which maintain a good performance for the whole spectrum on these unspecified or unknown parameters. Sometimes we don't know what is the variance of our normal distribution, and we want to come up with some statistical test which is good all the values of this unknown parameter. And this composite versus simple distinction is extremely important, and I think we will discuss it a couple of times when we continue discussing this paper. But our listeners need to understand that here is a very, very important point.
Yes, and that's exactly what we call nowadays uniformly most powerful test, and that's the Neyman and Pearson lemma that we learn in statistics.
Yeah. And this is by the way, if we're talking about the first course of I don't remember calculus, you have point convergence, and you have uniform convergence in the interval, and these are simple and composite. These are very related points, because if you have a simple hypothesis, you know everything. You want to discuss a kind of convergence at a single point, and in the composite case, you are talking about uniform goodness, something like that.
Yeah.
Interesting. Okay, I'll continue. So now with the part that they talk the actual likelihood ratio, right? And they denote by the ratio gamma, right?
It's lambda.
Lambda, yeah. I knew my.
Isn't it alpha?
Lambda. Yeah, lambda. Yeah. The ratio between the probability of the hypothesis, the null hypothesis, divided by the what they call it's gamma. Again, I don't know.
It's omega.
Omega. Thank you, man. Thank you, Nir. Sorry. Yeah. And omega, it's like the whatever. It's not the null hypothesis.
The alternative hypothesis.
Yeah, exactly. That's what I was looking for. The alternative one. And then they have two distinctions between a simple and a composite one. We won't go over here. But then they say, okay, now you're trying to solve the problem of deciding if you reject or accept. Then you need to choose a priori your, like what we said, the type 1 error that you accept or you feel okay to work with, right? So just to our listeners, type 1 error is what's also called the false positive, is when you reject the null hypothesis when it is true. Okay. So then let's say you choose that, let's say 5%. Okay, I want 5% of the times that I do that I will have a type 1 error. Then you go to a table. Back in the days, they have some tables, and they got a C constant. That's what you see here. And then they say, okay, if the lambda, am I right, is smaller than C?
Yep.
Then I think you accept. Let me read it. Let's read it.
Yes.
The use of the principle.
Okay.
Yeah, the use of the principle of likelihood in testing hypotheses consists in accepting for critical regions those determined by the inequality. Okay, you had a question?
No, I don't have. There's a very important sentence after the previous formula.
Tell me which one.
Yeah,
I'm skipping.
I will read this sentence. Under this condition, the upper bound pi gamma is often a maximum of 13 for fixed values of x's with regards of all possible systems or possible values of alphas. Here he's talking about uniformity. This alternative hypothesis should hold for all possible values of these unspecified parameters, which we assume that we don't know. And here we see that in the composite case, the things are much more complicated as we need to get some uniform estimate over all the possible values of these unspecified parameters.
Exactly, yeah.
It shows that the problem is much more difficult.
Yeah.
It is much more difficult, yeah.
Okay, here he's talking about again, type 1 and maybe type 2 errors, right? So type 2 is when it's like a false negative, is when we fail to reject the null hypothesis when it is actually false.
I think it's type 1 and type 2. Yeah. Sorry.
Yeah, that's what is usually in the paper also later.
Yeah.
Talks about
in radar, we call it false alarm for type 1 and misdetection for type 2.
Okay, cool. Yeah, so different disciplines had different names, right?
Yes.
For the same idea. And here he says, those two errors, we're reminded of the old problem considered by Laplace of the number of votes in a court of judges that should be needed to convict a prisoner. Is it more serious to convict an innocent man or to acquit a guilty? That will depend on the consequences of the error. Is it the punishment, death, or a fine, etc. Right? So it's similar again.
Yeah.
Each problem a priori, we should choose what's more important, the type 1 or the type 2, and then we should approach. It will give us some a priori inputs to the problem.
Yeah, and by the way, it's the same. This is a nice example, but it's the same in radar. When you employ a radar that shoots a missile out of the sky, you say, what's more important to me? That sometimes I will shoot a missile and there is nothing to shoot down, or that I miss a missile that is coming in and people will die. Same with autonomous driving, right? Do you miss a child crossing the street? That's more. I think that's more harsh than thinking that the child is there and stopping the car when there is no child there, and so on.
I would second that, because I think this whole part is why it's important not just understand the math as a mathematician or data scientist or statistician. You need to understand that before you even write anything, think about the problem you're trying to solve, what you're trying to solve, which are your assumptions, etc., to formalize better what you do later with the actual math or computation in our days.
By the way, can you go scroll up to equation 12? And I just want to re-emphasize that this equation, number 12, no, 14, sorry, 14,
yeah,
is 14 is the likelihood ratio test. Period. That's it.
Yeah. And the constant is derived from the type 1 error.
Yes, the false alarm. Yeah.
You get it from a table, and then you calculate the likelihood ratio.
Yep.
And you're ready to go.
This is the first time that it was ever introduced to the world.
Perfect. Now we move to the case of the simple hypothesis, right? So simple hypothesis is we have some distribution and everything is known in a sense. There's no variance or no parameter that is varying. And it says here they define the P0, P null of omega 0 that is equal to an epsilon. Again, this is the type 1 error, right? So we started by defining a priori what we accept as a type 1 error. Let's define it as epsilon. Okay, again, rejecting the null hypothesis when it's actually true. That's why it's P0. And then, okay, so he says, or they say, following the ordinary method of the calculus of variation, the problem will consist in finding an unconditional minimum of the expression of, I'll just say at the beginning, P0. So again, the type 1 error minus K, the type 2 error, which is P1 of omega 0. So we're trying to minimize the type. This eventually it's integrals here, but from a conceptual point of view, we chose a priori the type 1 error, let's say epsilon. Now we're going to have some type 2 error. Let's try to minimize it.
Yes.
To use the calculus of variations. Make sense?
Yeah, it's kind of like Lagrange multipliers. Yeah.
Yeah, it's exactly right. Am I wrong?
Yeah.
It's that's what I learned. I never learned calculus of variations, but I learned Lagrange multipliers.
Yeah, when they proved the Neyman and Pearson lemma in my class, they used Lagrange multipliers, maximizing 1 minus P1 while keeping P0 constant. That was the constraint. But it's the same. It's the same.
Looks the same.
Yeah.
Yes.
And again, there's now a lot of derivations and illustrations, but I think that was the important part. Let's go to the examples.
Wait, a second.
Tell me if you have something important.
Go up. That's it. Here in equation 24, 25, they proved for the simple hypothesis that the ratio test is the most powerful or the most efficient test. So now they're not just talking about likelihoods, they actually prove it.
When they define efficient is the one that minimizes
the type 2 error while keeping the type 1 error constant.
Exactly, given the type. Yeah, perfect. Yeah. Thank you for pointing that out.
Yeah. So they solved the integral and they proved it. That's number 25.
And this famous lemma?
That's the Neyman and Pearson lemma. Yeah. The most powerful in a simple case, and in composite case, it's uniformly most powerful, like you said before.
Okay.
By the way, just a question to you guys. I never encountered in real problems of engineering the simple case. Did you? I always estimate the standard deviation and the mean, or I put the mean to 0 and estimate the standard deviation or the variance.
Yeah, when you do estimation problems, by definition, it's composite, no?
Yeah.
Because you have like a parameter.
This is not composite. This is not composite. This is how did they call it? How did they call it? Composite?
No, so there's the simple one and the composite one.
Okay.
Composite one, you have some unspecified parameters which values you don't know. For example, you are trying to estimate the average of some distribution for a known variant.
Yes. Okay.
Yeah, so here's a simple one. Let's look at the simple case. We have a Gaussian distribution with a standard deviation sigma 0, and alpha 0 is the mean of the population. Okay, so, that's the null hypothesis. That's the mean is equal to alpha 0, and the standard deviation is sigma 0.
Yeah. In other words, they have the same variance but different means.
Yeah, exactly. It says the mean being unspecified, but sigma, the variance, always equal to sigma 0. And alternative hypothesis H1 is when the mean is alpha 1. So they have two Gaussians, one of the mean alpha 0 and the other with a mean alpha 1. That's the two hypotheses.
It's
But
A, no?
the sigmas
By
are
the way, it looks like A to me.
It looks like A. It is
it's
not
maybe
like
A,
alpha,
okay.
but it looks like A, yeah.
Okay. A and the
Mike, I think that Daniel is in Greece now.
almost. I'm not far from Greece. So in order not to get doxxed, I won't tell the country element.
Okay.
And now they do the likelihood ratio between the two distributions, and they say it's equal to some K. And then they continue to get the inequality.
Yeah,
right?
the test.
If we're above some, the test, the Pearson Neyman test for this case. Okay, and here they show a plot of the Gaussian distribution and the type 1 error. Shows it 5%. So this is maybe similar to like a p-value in a sense.
It is connected, let's say.
Connected, yeah.
That's also called, by the way, they call it the size of the test, this epsilon.
Okay.
Okay, and then here you have another few minutes, right?
Yes, we have 5 minutes.
Yes.
Okay, so I want to jump to the end so we can go over the conclusion and final remarks.
Just another addition. They subsequently prove that for composite hypotheses, likelihood ratio test is still the most uniformly most powerful test.
Yeah, here now the composite hypothesis.
Yeah.
But it is more difficult to compute, right? Because you need to somehow integrate over all possible values of these unknown parameters, and you need to assume some distributions, some assumption about these unknown parameters. So it is complicated.
They say that if you assume distribution, then it's like a Bayesian type of classification problem. But they don't do that. They just estimate it like maximum likelihood estimation.
Yeah.
We are going over like pages of derivations and integrals to the people that.
And by the way, I think they're computing the maximum, as far as I remember, it is a quite long paper. They're computing the maximum of this likelihood function under these unspecified parameters. They're computing derivative or gradients according to these parameters, and they're trying to estimate this alternative likelihood as a maximum out of all possible values of these unspecified parameters.
Yes.
This paper is not so easy. It is complicated.
No, it's not. It's not that easy. But in a summary, it's just the maximum likelihood over the whole parameter space. Yeah.
So let's see what they say. We're to chapter number 11. We jumped a little bit. Summary of results.
This is 6, not 11. But
sorry. Yeah, it's not an X. It's a bit better. We jumped less than you think, guys. Listening. Okay. So number 1, they give 6 results. And number 1, a new basis has been introduced for choosing among criteria suitable for testing any given statistical hypothesis, the null hypothesis H0, with regard to an alternative H1 or HT. If theta 1 and theta 2 are 2 such possible criteria, and if in using them there is the same chance epsilon of rejecting at 0 when it is in fact true, we should choose that one of the two which assures the minimum chance of accepting H0 when the true hypothesis is HT. So again, if you have 2 hypotheses, choose the one that minimizes error type 2, given you chose an epsilon, which is error type 1.
Or maximizes the test power, which is 1 minus type 2 error.
Yeah.
Perfect. And starting from this point of view, since the choice of a criteria is equivalent to the choice of a critical region or multiple space, it was possible to introduce the conception of the best critical region with regard to the alternative hypothesis HT. This is the region, the use of which for a fixed value of epsilon assures the minimum chance of accepting H0 when the true hypothesis is HT. The criterion based on the best critical region may be referred as to the most efficient criteria with regard to alternative HT. Right, Nir? So this is what you said. They actually proved that the maximum likelihood is the most efficient.
Yeah.
Number 3, it has been shown that the choice of the most efficient criteria or of the best critical region is equivalent to the solution of a problem here in the calculus of variation. We give the solution to this problem for the case of testing a simple hypothesis. To solve the same problem in the case where the hypothesis test is composite, the solution of a further problem is required. This consists in determining what has been called a region similar to the sample space with regard to a parameter. So again, a parameter is the thing that can vary and is unknown. We have been able to solve this auxiliary problem only under certain limitations, limiting conditions. At present, therefore, these conditions also restrict the generality of the solution given to the problem of the best critical region for testing composite hypothesis. So I said they solve it also only for some cases. Number 4, an important case arises when the best critical regions are identical with regard to a certain class of alternatives, which may be considered to include all admissible hypotheses. In this case, which, as has been shown by several examples, is not an uncommon one, unless we are in a position to assign precise measures of a priori probability to the simple hypothesis contained in the composite null hypothesis. It appears that no more efficient test than that given by the best critical region can be devised. So did you follow that one? They talk about a priori again. So this is, again, the composite case. We have an unknown parameter.
Yeah, if they assign the a priori probability, then it's a Bayesian problem. And they show it in the paper.
Cool. Number 5, the question of the choice of a good critical region for testing a hypothesis when there is no common best critical region with regard to every alternative admissible hypothesis remains open. It has, however, been shown that the critical region based on the principle of likelihood satisfies our intuitive requirements of a good critical region. So they say there's some alignment between what we intuitively think and the results. And last one, number 6, the method of finding best critical regions for testing both simple and composite hypotheses has been illustrated for several important problems commonly met in statistical analysis. Owing to the considerable size which the paper has already reached, the solution of the same problem for other important type of hypotheses must be left for separate publication. Yeah, it was 50 pages of math and derivation. But cool. Let's give a few words to summarize. Nir, before you leave.
Yeah, so for me, this is first, this paper builds on Fisher, the maximum likelihood criteria. And then it uses this maximum likelihood criteria to say, okay, intuitively, let's compare the likelihoods, how? Ratio between the likelihoods and compare it to some threshold that we are calculating by fixing the false alarm or the type 1 error. So, okay, this is not just happy intuition. This is actually grounded in math. And this is the contribution of this paper. And this paper, to me, in my eyes, was introducing all of the basis for classification theory and machine learning and AI.
And some small observation from me. This paper for me, I will be talking not from very mathematical angle, was for the sake of change or some change, because I'm always talking about math now. Now I'm not going talking about math. This purpose underlines the importance of choosing these both hypotheses, this null hypothesis and this alternative hypothesis, because this critical region depends both on your null hypothesis and also on your alternative hypothesis. If you change at least one of them, the critical region would change. Also, would also change. So then you are choosing your hypothesis. Think about what is null hypothesis. Then even more important, think about your alternative hypothesis, because it is crucially important.
Yeah, I agree. And this is the place where we are, as practitioners, use, our judgment in a sense, right? So we bring the non-mathematical part in solving problems. And that means understanding the business case, if you're working, or, understanding what you're trying to achieve, what's the goal, what we're trying to measure, etc. All of this. So I like it. That's my contribution to the non-mathematical part.
By the way, this test is used everywhere these days, in every field of science.
Yes.
Okay, so that was lovely, guys. Thank you very much, and see you next week.
Thank you, guys.
Thank
Take
you.
care. Enjoy the trip, Daniel. Bye-bye.
Thank you.